Okay, it's now time to talk about some common things with rotational motion. We're going to do moment of inertia for point masses and non-point masses. And then we're going to talk about angular momentum and rotational kinetic energy. So let's get started. Well, as we talked about before, in any kind of motion, there should be resistance to change in motion. So there should be resistance to change in motion when something tries to spin. So here we have a sphere of mass m, and we have a point of rotation here, and let's say we have a very light rope here, and we're going to want to rotate this thing in a circle. Okay, so we need to get the moment of inertia for this. There should be a resistance to change, okay, in angular motion for this, so we're going to give it the letter I. Well, it turns out the formula for this, and this will be the general formula for moment of inertia, it's going to equal m times the radius squared. So the distance to the point of rotation will give the letter r, and the mass will give m. So moment of inertia is Newton's first law as it applies to rotational motion. So if I want to figure out the resistance to change in angular motion for this particular sphere, I'll multiply it by its mass times how far it is from the point of rotation. Now, why do we want to do that? Well, let's go back, okay, in non-rotational motion. We said force is equal to mass times acceleration. So this would be Newton's second law. So if I apply a force to cause something to move in a straight line, that'll equal a product of the mass times acceleration. So as mass goes up, the acceleration goes down. Well, how does that relate to rotational motion? Well, rotational motion is caused by torque. We give that the Greek letter tau, and we know tau is equal to force times the distance to the point of rotation. So if I apply a force on this ball here, that's going to be the radius then. And we'll assume that it's a perpendicular distance to that. So the torque is equal to force times radius. Okay, so but what does that equal? Well, let's take a look at this. We're going to say torque is equal to I times alpha. And see how that relates to our force equals ma equation. Your torque, though, is going to be force times radius. And I has to be calculated for every system then. The moment of inertia has to be calculated for every rotating system. You can't just simply use mass like we did in linear motion. And then alpha is our angular acceleration that we were talking about, okay, in our beginning part of rotational motion. So that's how Newton's first law and Newton's second law relates to angular motion. So if I give a certain force applied to the edge here, we can calculate the torque. We need to calculate the moment of inertia, and then we can solve for the angular acceleration. So that's why we need a moment of inertia. Now, what if I don't have regularly shaped objects? Let's say I want to spin this bowling ball on its axis of rotation. So I'll just do a little dash lines here to indicate an axis of rotation. So we're trying to spin this in this direction here. Well, the equation becomes more complicated, and we use integral calculus to solve it. But for now, we'll just reveal answers. The moment of inertia, I, for this rotating sphere, and this is for a solid sphere, is equal to 2/5 mr squared. Okay, and we're not going to go through the calculus of what gives us that. We're just going to talk about that. That's the end result of that. Now, what about this? The old merry-go-rounds with the bars on it, and the children would stand on it or sit on it, and this thing would spin around. You know, what if I was to apply a force to the edge of this, and I'll just kind of draw that in there, and I'm going to try to make the spin. Well, if we simplify it to this system here, we're going to ignore these bars here because the bars are more complicated. Well, we would need to know what the moment of inertia of this is. So moment of inertia I is equal to 1/2 mr squared. And again, we would use integral calculus to find that, and we're not going to go through the calculus of that. So what I need you to realize is that each system has its own unique moment of inertia equation. You know, what about a long thin rod or a long thin plank here? Let's say we rotate it about an axis in the middle, so this is rotating around like this. Well, I for that is going to equal 1/12 ml squared. L being the total length of this thing. So L, let's see if I can, choose an arrow to do that to show it to you. Okay, and L would be the length from here to there. And let's go ahead and label that L. So you see the equation changes depending on, what system is actually rotating. And all those equations will always be provided for you. So you don't need to worry. So you don't have to do the calculus in this particular chapter. Now what if I apply something here? So let's say there's a child actually standing on this. Well, then we have two different kinds of rotating systems here. So let me just draw the child here. Do a quick stick figure here. You guys know my incredible ability to draw, so here we go. So now we have a rotating disk. The moment of inertia of that is still going to stay the moment of inertia of 1/2 mr squared. But this person here is acting like a point mass, kind of like the sphere in our first example. This person's whole body is going around something else. So it's not rotating about an axis through the person. The whole person is going around. So the moment of inertia of the person is still going to be I equals mr squared. So I want to point that out to you, that if the whole object is going around something else, it's still treated like a point mass. Now, why do we call them point masses? Because all of the mass of the object is going to look like it's coming from one point, okay, inside the person. And that's how we deal with moment of inertia, or resistance to change in angular motion. So for all these systems, we would use the equation torque equals I alpha. If I were to give you an applied force, you would calculate the moment of inertia, and then you would get the torque, and you'd be able to calculate the angular acceleration for the object. And that's how we handle it. In our next video, we'll complete our discussion about rotational kinetic energy and conservation of momentum.